All right, so continuing where we left off, we were talking about converting from polar to rectangular coordinates. Now we're going to go the other way. So our first example is, no, I'm sorry, we're still doing polar to rectangular with example A. I got off, my bad. Okay, so 3 pi over 4 is the polar coordinates for that point. So x is r cosine of theta, and y is r sine of theta, where r is 4 and theta is 3 pi over 4. So the cosine of 3 pi over 4 is negative square root of 2 over 2. So that simplifies to be negative 2 square roots of 2. And sine of 3 pi over 4 is positive square root of 2 over 2. Simplifies to be 2 square roots of 2. All right, so that means that our point in rectangular coordinates is negative 2 square roots of 2, comma, 2 square roots of 2. Now just a quick sketch to sort of make sure everything's looking good. 3 pi over 4 is of course in the second quadrant. And we're going out 4. So about right there. And if I were to go negative 2 square roots of 2 and then positive 2 square roots of 2, that certainly seems like a logical placement for that point. And unless I've made a mistake with a particular numerical value, that does appear to be correct according to the graph. Okay, so this is the one I was thinking we were on already. My apologies again. This one we're going to change from rectangular into polar. So we know that x is 3 square roots of 3, and we know that y is negative 3. So r squared is x squared plus y squared. And I kind of like having the r written on the left side since that's what I'm solving for. I'm used to thinking x squared plus y squared equals r squared, but I think this is probably better. All right, so 3 square roots of 3 squared is 9 times 3 is 27, plus the square of negative 3 is positive 9. 27 plus 9 is 36. And so that means that r is plus or minus the square root of 36, which is 6. Now remember, this is very different from what we did in trigonometry in your pre-calculus course. R was only positive in that world. But in this world, the polar world, r can be negative, so I have to allow for both possibilities. Then the tangent of theta is y over x, so that's negative 3 over 3 square roots of 3. Which simplifies to be negative 1 over the square root of 3. Which, if I think about a triangle where that could happen, I'd want the y value of the trigonometric idea, tangent theta is y over x. I'd want the y to be negative 1 and the x to be square root of 3. So this point right here for my right triangle. Or it could be, in fact, that it's 1 over negative square root of 3, which would be positive 1, it's right there, and negative square root of 3, it's right there, giving us this reference triangle. And so if you know these right triangles, this is a 30, 60, 90 right triangle where the reference angle size is pi over 6. So if we use the fourth quadrant angle, we could call that negative pi over 6. If we want to use the second quadrant angle, that could be called 5 pi over 6. So there are a couple of our options because we have a lot of them. So what we're going to want to do here, because we have a lot of possibilities, is we actually want to plot that specific point, 3 square roots of 3, 3 square roots of 3, negative 3. Let's just say it's right there. Well, to me, the simplest thing to do would be to use a positive r and angle like negative pi over 6. But you got to look at the directions, and I can't use those. I have to use an angle. Let me draw a ray here so it's easier to see where we're headed. I'm trying to find an angle that represents that terminal side. And so since it has to be between 0 and 2 pi, we're going all the way around like this. And so that angle is 11 pi over 6. Because of the directions. Oh, but wait, r is negative. Oh, well, I guess I should have read that first, huh? Well, if I want r to be negative in the points in the fourth quadrant, that means I'm going to have to go backwards and find an angle between 0 and 2 pi for the ray that stops pi away from the ray that contains our point. So since the reference angle is pi over 6, that means that the theta I'm going to use is 5 pi over 6 if r is negative, because they told us it would be for this particular problem. And so that means that our answer for this one is negative 6, 5 pi over 6. So make sure you read the directions. I was even caught a little bit off guard for a second because I hadn't really paid attention to where I was headed that well and didn't actually get the right answer at first. I had to really think about that carefully. Now, as luck would have it, which is really good, part C, it's really the same information. It's just that this time our angle being between 0 and 2 pi is the same idea, but this time we want the positive r. So in this case, we're going to use the positive 6. And now the work that we thought through earlier actually pays off. If we're going to use positive 6, that angle of 11 pi over 6 was what we originally thought through, so it wasn't wasted effort, just misplaced effort. And that would be the coordinates of that point. Right. Move this down a bit. Oh dear, I hit something wrong. Let's see if I can figure out where I am here. Let's see. There we go. Okay, I am so sorry. Hit the wrong button. Okay, so here we go. Now, not only can we convert the coordinates of a point from rectangular to polar or from polar to rectangular, we can also convert entire equations from one form to the other. So this is now example 3, problem A. So we have a whole equation of points, r equals 3 sine theta, that we need to convert into a nice rectangular equation. Well, we're going to use the same 4 equations that we talked about earlier to do this. Now going from polar to rectangular, I'm going to tell you I have two tricks. One is to multiply both sides of the equation by r. The other is to square both sides. And it kind of depends on what you have to begin with. You see that sine theta there? It would be really nice if it had an r in front of it, because the r sine theta I know is the same thing as y. So in this case, multiplying both sides by r actually helps. So that becomes r squared equals 3r sine theta. Then rewriting that in rectangular form, I know that r squared is x squared plus y squared. And I know that r sine theta is y. So that's appearing to look like the equation of a circle. And I do want you, when you recognize a conic section, to go ahead and rewrite that in standard form. So to write that in standard form, I'm going to move that y, that linear y term, over to the left side to be with the y squared term. Leave a little space. We'll see why in a second. Then I'm going to complete the square on y. So half of -3 is -3 halves, squared is 9/4. So I'm going to add 9/4 to both sides. And then do the factoring. That becomes x squared plus y, the quantity y, minus 3 halves squared equals 9/4. And I know the directions don't say so, but I'd like to expand this one just a bit further. We know that this is the equation of a circle. Because it's in the standard form, we can identify the coordinates of the center. They are 0, 3 halves. And the radius of the circle is the square root of 9/4, i.e. 3 halves. So if I were to graph this in a rectangular way, I would get a circle centered at 0, 3 halves. Let me allow myself a few marks here on that direction. I'm going to put the center at 0, 3 halves right there. And the radius is 3 halves. So I'm going to move from that center point up 3 halves, down 3 halves, left 3 halves, and right 3 halves. So up 3 halves puts me here, down 3 halves puts me there, to the left 3 halves puts me there, to the right 3 halves puts me there, and this is a circle centered at 0, 3 halves, whose radius is 3 halves. Now if we'd done a whole lot of equations like this, we would find that actually graphing this in a polar form is not hard. I mean, technically, if we're going to graph an equation r equals 3 sine theta, we should be making a table of values from 0 to 2 pi using almost all of your special angles that you know, calculate the r, and plot all those points. Kind of a little laborious thing. But this is a nice one that you should recognize and use in a good way. Whenever you see r equals sine theta, this will be a circle its center will be on the y-axis. And the way I'm going to remember that it's the y-axis that the center is on, I can't write that S, I'm just kind of almost off of the screen. Pretend like I wrote an S there. Is that sine of theta is y over r, so sine is related to y. So center on the y-axis, and the diameter of the circle not the radius, but the diameter is A. Oh, and one other point, the origin is a point on this circle. In other words, the pole is a point on the circle. Okay, so if it's centered on the y-axis, one of the points on the graph is the pole, and if I go up A, so up 3, that'll put me at that top point of the circle. And then, of course, the center's halfway, so you could take half of A to find out what the coordinates of the center are, in this case 0, comma, A over 2, 3/2. And then just go that radius from the center 3/2 all the way around, just like we did. So that's actually a pretty nice set of coordinates to know. Another nice way to kind of finish that out and make that look good is if you think about a couple of values. Wasn't going to do a bunch of points, but this is, I think, is worth it. If I have some theta values, oops, sorry, and some r values, and I calculate those, one of the angles I might have used is pi over 6, and another one is 5 pi over 6. And you may know that the sign of those are nice rational answers. The sign of pi over 6 is 1/2. So 3 times 1/2 would be 3/2. And the sign of 5 pi over 6 is also 1/2. So it's also going to have an r value of 3/2. So if you're graphing this in a polar world, you should be able to go to the ray that represents pi over 6 and go out exactly 3/2. So 3/2, that circle would be through there. That would be an easy point to get. And at 5 pi over 6, same thing. Go to the ray or the radial line that goes through 5 pi over 6, go out along it 3/2, and that would be a point on there. And again, that would be along that circle that's 3/2 away from the pole. And so those are points you should be able to get. Definitely get the point that is at the pole, the point at the other end of the diameter of the circle on the y-axis, so 3 away, that point up there on the y-axis at 3. And then these two values are really easy to get using values of theta that give you nice answers for for sine of theta that are nice rational numbers instead of square root of 3 over 2 or square root of 2 over 2. I'm trying to avoid those. Now, as it turns out, I'm kind of going beyond the scope of this one question, but I think this is worth talking about. If you had an equation of the form r equals a cosine theta, a whole lot of what we just talked about is going to be true. You will get, this graph will be of a circle, for sure. The center this time, however, will be on the instead of the y-axis, the x-axis. And again, how am I going to remember that it's the x-axis? Well, because it's cosine. Oh my gosh, what's going on? Getting all these notification pop-ups. Okay, hopefully you're not seeing those. The center will be on the x-axis. And again, we'll know it's the x-axis because, oh my, now my pen's not working. Hold on. Okay, there, it's working. The center will be on the x-axis, and I know that because it's cosine that's in this equation. and cosine is related to x. The diameter will be a. And one of the points will be, that's on the circle, will be at the pole. So let's do one of these quickly, graphing it using what I just talked about. You should still be able to convert the equation from polar to rectangular. Again, multiplying both sides by r for a particular example would be good. Let's graph r equals 5 cosine theta. So if we're going to graph that, draw the polar grid this time so that it's clearer than the one that I did before with the sign. This will clarify a lot of what I said up there better, to have this grid available. All right, so since it's in this form, r equals a cosine theta, I definitely know it's a circle. One of the points is the pole. And since it's cosine, I know that the center is on the x-axis. So I'm going to go a distance from the pole of 5. 1, 2, 3, 4, 5. That's the diameter of the circle. So that point I just graphed is also a point on this circle we're drawing. Now, to go up the radius and down the radius is actually not easy when you're seeing the concentric circles. So I'm going to suggest that we use a couple of special angles here. I'm going to consider pi over 3 and negative pi over 3. And I am thinking about those on purpose because I know that the cosine of those gives me a nice rational answer. For example, the cosine of pi over 3 is 1/2. So 5 times 1/2 will be 5/2. And the cosine of negative pi over 3 is also 1/2. 5 times 1/2 is 5/2. And so if I go to pi over 3, go to that radial line, pi over 3, I'm going to go out 1, 2.5. And at negative pi over 3, go out 1, 2.5. And those are 4 of the points that are on my circle. So I'm going to graph through those points and trying to make it look circular. Do the best you can. You're going through those points and making a circle. Like that. And so that's how you can graph r equals a sine of theta or r equals a cosine of theta with a lot of ease. Alrighty. The next one that we're going to encounter, example 3, part B, is we're converting from rectangular to polar. So let me get this. This is part B. X equals the opposite of y squared. Okay. And this is in a lot of ways easier than the other way around, because if you have an x, you can always replace it with r cosine theta equals the opposite of, and you can replace every y with r sine theta. So that substitution is easy. And now simplifying, that becomes the opposite of r squared sine squared theta. Now earlier I said I had 2 tricks when I'm going from polar to rectangular. One was you could multiply both sides by r if you need to, which means here we could divide both sides by r if we wanted to. or we squared both sides. Here we could take the square root of both sides. The reason we're trying to do that is just like with functions y and x, you usually want y to be written as a function of x. The big exception to that are the conic sections, which are quadratic equations in x and y. It's like x squared plus y squared equals 25. That's not y equals something. It's not that explicit form. But most of the time, that's what we want. Well, by the same token, we usually want to have r equals a function of theta. That's kind of the ideal situation. There will be times where we can't solve for r explicitly, just like x squared plus y squared equals 25. We generally don't solve it for y, but we just graph it from that standard form for a circle. There'll be times where we don't solve for r. But in this particular problem, we can, because we could divide both sides by r and get cosine of theta equals the opposite of r sine squared theta. Then, if we were to divide both sides by the opposite of sine squared theta, we would be solving for r. Which is kind of what I said we wanted. And then we'll simplify that. Positive divided by negative is negative. Excuse me. Cosine divided by one of those signs is cotangent theta. And 1, which is what's left in the numerator, divided by the other sine of theta is cosecant of theta. And so this is a polar equation for that x equals the opposite of y squared. Okay, so example 4. Moving this, sorry, takes a long time sometimes. Oh, you know what? We're at the end of the page. This is actually a good place to stop. So let's stop here and we'll pick up with the next section.